Hi. So after convolution, we also need to know a little bit about max pooling. And max pooling is super simple. It's essentially ReLU in 2D. What I mean to say is, what max pooling does is it reduces the size of your input features. So the output is of lesser size than your input. And what is happening here is you have your input of size 4 cross 4. So these are, let's say, 1, 2, 3, 4 and 1, 2, 3, 4, right? So it's a 4 cross 4. And as output is size 2 cross 2. Yeah, and all that I'm doing is I'm taking, let's say, so I'll show you maybe in the next one what we are doing. So what we are doing is, let's say this is what our 4 cross 4 image looks like, right? So this is what our 4 cross 4 image looks like. Yeah, let me maybe rub this off. Okay, so this is what our 4 cross 4 image looks like. And then what are we doing to that 4 cross 4? We have a kernel, right? We have a kernel of size 2 cross 2. So this is called your max pool size. And in max pool, we usually have non-overlapping. So the stride is 2 because of that, because the size of the kernel is 2. So this is the size of your kernel, right? So this is the size of your max pool window, the max pool kernel. And we have a stride of 2. So you have this window. And in that window, you choose what is the maximum value. And this happens to be the maximum value, right? Then you move that window next. And what you do is you copy this to the output, right? So you copy, so your output will have the first value as this. So this is your first value. Then you move your window, you take the maximum value, you put it as the next. There's nothing, no more to move because your size of your window itself is 2 cross 2. Then, and it's not overlapping your stride, both in X and Y are 2. So you come down, then you take your maximum here and you put it here. Then you move one step right and then you take your maximum here and you put it here. And that's it. That's the max pool operation. And as you know, if you write it down during backprop, what will happen is you have your gradients, right? And the gradients essentially, it's a gating mechanism, meaning only the gradients corresponding to the non-zero value propagate. So the output will have gradient of size. So the output is, 2 cross 2. So you have 4 gradients coming in, 1, 2, 3, 4, right? But here, you have, let's say, size 4 cross 4. So you have a size 16 here, right? So but now in 16, what will you do? You have your 16 here, right? And that 16 is divided into this 4 cross 4. So you have 4 here, 4 here, 4 here and 4 here. And remember, this one was the output, this one was the output, this one was the output, and this one was the output. Everything else was 0. So you take this gradient and you pass it in this location and everything else is 0. You take this one and you pass it to, then the whichever it corresponds to, right? So this one corresponds to, so let's now just do this 2 cross 2. So whatever gradient you got here, you pass it here. Whatever gradient you got here, you pass it here, right? Because this was the only non-zero element. Whatever gradient you got here, you pass it here. Whatever gradient you got here, you pass it here. Every other gradient, is all 0. So everything else is 0. So what this layer passes to the previous is, of course, of size 4 cross 4, but it's this sparse matrix with only 4 values and the rest of the 8 are all 0. So these 1, 2, 3, 4, 5, 6, 7. So this is 16 minus 4. So the remaining 10 are all zeros that we pass to the previous layer. And that's all that there is in max pool. Why do we use max pool? Because we want to reduce the size, right, as we go down further. And the intuition of max pool is that, okay, you're trying to find the feature that actually gave you a high activation, right? So you had your kernel and that kernel for that one location gave you a high and you're only interested in what location gave you the high, right? So then you're kind of doing this max pool to only take that high activation because you're not interested in anything around it, right? So you're doing this max pool and max pool reduces the size of the image. There are other kinds of pooling. I mean, it's not required here, but there is something called as average pooling. Then there are also ways to do it without pooling, right? You just do convolutions with stride and then that kind of reduces the size of the image and people don't do any pooling there. This is transposed convolution. Again, because we're doing convolution, this is something you should know, but I won't worry about it too much. And the way to think about is to think that, okay, this convolution is kind of wired up in the opposite direction. Meaning instead of doing the forward prop, we're actually doing the backward prop. And instead of doing the backward prop, we're actually doing the forward prop because it's still a convolution. And this actually increases the size of your image, right? So transposed convolution is just that, and people used to use it for semantic segmentation kind of approaches. Network of this kind of this kind of a size is called a U-net, right? Because it's like a U. So in semantic segmentation, what you need is, you need the output size to be the same as input. So your output size needs to be the same as input, but we want to still go down because that helps with your, the reducing the size of parameters in your image. It also helps with kind of creating this bottleneck, the higher level features, all of that. But then how do we go up back again? So you can go up back again by doing either like a nearest neighbor upsampling or using these so-called deconvolutions. I'm not going into detail, but this, if you write it down, what is most interesting is it's actually the backprop of convolution, right? So it's the backprop. And there's an animation here, you can look at it, you can read about it, we will write below the lecture, but I wouldn't pay too much attention or importance to it just because people don't use it as much these days. And it's anyways, the time for transformers, and we're going to do transformers very soon. There is also this so-called depth-wise separable convolution. Again, something you should know and something used by the exception or the MobileNet network. And this kind of reduces the compute, how much computation you need to do, because otherwise convolution, though has fewer parameters, it's computationally a very expensive operation. Now, this is again something that I really want you to understand, right? And this is this is where everything is in some sense a convolution. And what we are going to do is we're going to implement a fully connected layer using convolution. And let's see how. So what you usually do in a convnet is you start with some higher size image. In this case, it's 3x3. You do convolution. Convolution itself will reduce a little bit of your size because of the border effects, because the output size is size of input minus size of kernel plus 1. So it's 3x3, size of kernel is 2x2. So 3 minus 2 plus 1, we get a 2x2 as output. Now, usually what you do is, you do it a few times, and then finally whatever you get, you would get usually like a volume like this, right? You would flatten all of them. So in this case, we are just flattening these two numbers. So we get 4 numbers, right? Here you see more, but let's just make it 4. 1, 2, 3, 4. So this from 4, we are going to 3. So here we have 1, 2, and 3. And from finally 3, we are going to 2. Yeah, simple, right? Now let's see what happens, right? So now suppose we were to do this using convolution layers, right? Suppose we want to implement this fully connected. So here we have a fully connected, right? Here we have our weight matrix and here we have our weight matrix. Remember, here we have 4, here we have 3, and here we have 2. So now let's see how we can do this using a convolution operation. So we had our first convolution. And now in the second convolution, what we want to do is we want to do instead of this fully connected, we want to do a convolution, and we want to do a convolution with size 1 cross 3 cross 2 cross 2. This one we have no control over because this is the number of input channels, right? Previously. As size of output, what we want to do is we want to have the number of output neurons, right? So here remember we have these 3 neurons. Here we have 2 neurons. Here we have 4 neurons, right? So as output, what we want is, so this is the number of output channels, and we will essentially have 3 channels here, right? And then we have a kernel size, which is the size of your entire input size, right? So our input size was 2 cross 2, and what it is doing is, it is essentially doing a dot product of this, but with 3 channels, right? So if you think about it, what does it look like, right? It is 2 cross 2, 2 cross 2, 2 cross 2, and then we take each of these kernels, we do a dot product, and that gets us 1 neuron, right? So this will get us this first neuron. We then take this, right? We do a dot product with this, and then that dot product gives us this. Similarly, we take this, we do a dot product, and that gives us this. So you can think of this fully connected as also a convolution with this kernel of size 1 cross 1, right? So these 1 cross 1 convolutions are special. Now here again you can do the same. So there were these three outputs, so you don't have any control over this. Your output size is 2, so that is why you choose 2, and we want to do these 1 cross 1 convolution. And if you think about this, so this is again 3 times of size 2 cross 1 cross 1, right? So you have these 3, so you have 2 times these vectors, right? So this is, let's say, your w1 and this is your w2, and what you're doing is you're doing a dot product with this and you're getting this, and then and then you're doing a dot product with this and then you're getting this. So these 1 cross 1 convolutions are special, and you can use, so essentially what you want to do is so instead of that flattening operation which we usually do, right, this one, what you want to do is you want to do a convolution with the same size. So the convolution kernel size is the same size as this, right? So your convolution with the height and width of the features just before the flatten. And the number of input channel is the number of input channels because you have no control over this, right? So this is your one. And the number of output channels is the number of neurons in the next layer, right? So you can also do fully connected with just the convolution layer. Now this is again like a very interesting example of this sliding window convolution, and I want to maybe do this live in one of our weekly sessions. So I'm not going to do this now, but this is again something that is very interesting, and this is my ICLR, actually it was 2014, so ICLR 2014 paper, and in this what we do is we can kind of do this operation using fully so instead of doing this flatten, right? So here we are doing this flatten. So whatever output we get, we get this 9 cross 128. We flatten into this, then we go from here to 512, 256, and final 4 for the final 4 classes, which happens to be your face, shoulder, elbow, and wrist. We can do a sliding window using a convolution itself, and in some sense it is essentially doing this fully connected, and you're taking your fully connected part of your network. So you're taking this part of your network and you're sliding it over the entire image, and for every position of your fully connected you get one value out. Here you only get these 4 values, right? But here you get these 4 channels and every position of your fully connected. So you're essentially taking your fully connected and you're doing a sliding window with this entire fully connected part of your network, and each position of that fully connected gives you one value in this heat map, right? And so you can get like a heat map out. And this is why we were the first people to do this heat map based human pose estimation using deep learning, and we created IP out of it. Mercedes came looking for this IP. I sold my US company, which was based out of the Valley in San Mateo, to Mercedes-Benz North America in 2015, came back to India, and this network is now part of a lot of these Mercedes cars that are being sold, and we can talk more about it again in one of our live sessions.